Okay, so with the primary simulations completed, we can now dive into doing some individual studies right across the top of the board here. So starting with sun hours, we can look at the history that we just run. So the history gives us, this configuration, this current setup. So we ran this one for the site, and we set the time specifically to the worst possible solar hours for our location, that being the winter solstice, December 21st. And so this is the most extreme case. This little target or inspect button right here allows me to see how many hours of daylight are on a surface. And again, that is going to translate to an understanding of just how much daylight we have. So you'll note on some of these northern and even northwestern facades, we have absolutely no daylight at all. If we run this again at a different time of year, like let's say the summer solstice, June 21st, we're going to have more, but this begins to set up some basic potential understandings on how and where the sun is hitting some surfaces. So let's close that one down. Let's go to the next one, daylighting potential. And again, I've already run that analysis, so I can go to view history. So on this, we are looking at vertical surfaces primarily. And what this gives us is a percentage score. Okay, so right now, 32 to 37% of what is close to 5,000 square feet on the surface falls in an area that we know has daylighting potential. In other words, we can use sort of a standard window configuration and have some reasonable daylighting values on the interior. So again, if I use that inspect tool, anything that is over 27% has strong potential for daylighting. Once I get into the 15 to 27 percentile range, we know that we need to do a little work with what the windows are, a higher window to wall ratio, perhaps a light shelf, something like that, that would help bring more light in. Once we get below 15%, we know that, look, we are not going to get good daylighting values. We are going to have to supplement, if we want anything beyond ambient lighting, we're going to have to supplement artificial lighting on the interior of those spaces. Okay, so let's go ahead and close that, and let's go to wind. Once we start looking at wind, so wind gives us, again, it gives us sort of this real-time feedback. But if we open up the fuller analysis, now this one took a while to run. This was about an hour and a half, 2 hours to run this one. Again, happened in the cloud, so it didn't slow me down or anything like that. But if we look at this analysis, what we can see are wind directions from an annual wind rose, and we can begin to get some ideas of what's happening with this configuration. So specifically, if we look just north of the site, and again, I'm wanting this configuration and this particular site to act like a park. I have a pretty serious dead zone annually, 1.2 miles per hour on the wind in a majority of this, which doesn't seem really like a terrible, terrible thing. But when we start to think about it, maybe it's not so good either. If our predominant wind direction during winter storms is north and south, this great big void right here is also going to generate a great big snowdrift. If we start thinking about that as wind around June, when we really need, some cooling effects on the breezes, we are not going to get anything in terms of wind that's going to help a cooling condition along that edge, even in this location further away from the building. So it's kind of a bummer to see that. Not really happy with that building configuration in terms of it helping this site as a park. Now, it would also be really nice to see more specifics. Again, where Springfield is, we have everything from 0-degree days to 100-degree days. So the summer winds are very different than the winter winds. And there's really no telling exactly that on an annual wind rose. But there is a tool right here that does allow us to upload specific wind data as an EPW file. What I need right now, though, is the ability to, find those EPW files and dial them in. Also, turning on importance allows us to get sort of a three-dimensional volumetric understanding of what exactly is going on with the wind. And in this case, wind coming out of the south, we have this sort of drop in grade, the additional buildings around, the trees on the site, and the building itself, all adding to this condition where wind is really dying down as it comes into what I was thinking would be sort of the major entry point park plaza for the building. And so maybe a few times a year we're trying to block wind, that's great, but often that's going to be creating some problems. Microclimate allows us, and this is one of my favorites, microclimate really allows us to see specific points what things are going to feel like. So, for instance, if we set September, right now, in terms of when I'm recording this, it's typically pretty nice outside. But again, if I add my inspect tool, what I'm getting at 3 o'clock in the afternoon is a more specific definition of what the temperature actually feels like. And so this is measured in UTCI, or Universal Thermal Climate Index, which is a combination of temperature, humidity, wind, and solar radiation. So it's not the actual temperature, this is the feels like temperature. And what I was thinking would make for, a nice roof plaza in September is awful. Even in the morning, it's not looking so good, let alone if we switch this to, let's say, July, where it starts to become an oven. So what I'm looking at on this is I really need more trees, always helps, more shade, but I also need to start thinking about, is there a possibility or an opportunity to start thinking about the building itself creating some shade on the site so that the park atmosphere is better than 100 degrees at 4 o'clock in July in terms of the sensation on site. If we go next to noise, again, there's sort of a real-time noise, and we can get an idea, and this is a fairly simple site. Low volume streets running on either side. If we look at the more detailed analysis on the history, we'll see the street noise coming. It's a little bit more noisy on this edge. In particular, as we start to look at this portion of the building, we're getting into this 55 decibel range. Here on the street, we're starting to approach what is more like a 75 decibel range. And again, 75 decibels is sort of that sweet spot. Below that, and we are safe for hearing. Above that, and we start to get in danger if we're exposed to it for a prolonged amount of time of hearing damage. So just looking at this edge of the building and this street, there is some noise issue. Perhaps not major, but enough for me to understand what this building edge is made out of, what kind of material is going to matter in terms of noise transmission into the building. If we go next to solar energy potential and we look at its simulation, what we are going to see is what potential we have for solar energy on the roofs. And I'm pretty sure I configured this one wrong for the overall project, because that put a solar panel on every roof of downtown Springfield. So we are creating 386 million kilowatts. So let's kind of zoom in here just a bit and let's select just the roof tops of our building, and that's going to give us much more reasonable data. So looking at this data specifically, we know that we're generating right around 140 kilowatts per square foot. Looking at some energy use data, national energy use data, we know that a museum is going to be right around 16 kilowatts per square foot, or 140,000 kilowatts per year for this project. So on this, roof, if we were doing 60% coverage, roughly about 7,000 square feet, we're looking at right about 116,000 kilowatt hours, or about 80% of the overall building energy used. So cost in Springfield, Missouri is we're roughly about 70 cents per kilowatt. So what that amounts to is about $10,000 a year in energy costs or a utility bill. A PV system is about $2.82 here locally. So it's about a $400,000 system. 7,000 square feet of PV, it's about a $400,000 system. So our solar panel gains, we gain about $8,000 back every year if that was covered. So again, simple math will tell us 17 and a half, 18 years for payback, assuming that pricing stays even for the next 17 and a half, 18 years, which we know energy costs are going to go up. So payback, is less than 20 years on this. Still, it's a tough sell locally, but you can start to see where that is narrowing down in terms of overall application of solar panels on roofs. Last one that we're going to cover is embodied carbon. And this gets a little bit interesting because this is a fairly complicated model to be built over the top of our massing to calculate carbon. So what I did for this, specifically if we scroll down, you'll notice this is grayed out. And the reason why this is grayed out, it's not going to run it because this form is a little bit too complicated. So quite simply, built a simplified version, similar massing, right? Similar amount of square feet, but just went through this in such a way that we can simplify the form down, which simplifies the structure, and it allows Forma to run an easier base calculation. So all of this happens in just a few seconds when you hit run analysis. And what you're going to see are some basic definitions. So, didn't want those basic definitions. We wanted to come up and look at our carbon distributions. So in order to run an analysis of the carbon, of embodied carbon, what we need to do is we need to select our massing and we need to define some basic parameters for the construction of this project. So with that massing selected, I can click on my definitions. Oh, not my definitions, but on my analytical properties. So I have this building type set to commercial, which helps understand the use. The envelope. Several modern buildings in our downtown area are using a panel rain screen, steel paneled rain screen. And popular construction for our area for a larger building is still a steel frame. So given those parameters, when we run an analysis, we are starting to see 572 kilograms of embodied carbon per square meter, which translates in the States to 53 kilograms of CO2 per square foot. And our national average is a pretty broad range. It's 20 to 100 kilograms per square foot of CO2. So we know we're not on the really high side, but we're definitely not on the low side of that either at 53. So as we move through our final options, our final design, we'll be looking at different ways to run this analysis, different building types, essentially these different definitions that might improve our carbon footprint.